The Voyager, one probe, the most distant human-made object in the universe, is still sending usable information back to Earth after nearly half a century of exploring the vast unknown. NASA's Voyager probe has transmitted what could be its final message, and it's nothing short of astonishing. What secrets lie within this last transmission, and what does it mean for the future of space exploration? The story begins with an ambitious plan in the 1970s when a rare alignment of the outer planets set the stage for one of NASA's most daring ventures. Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that a single spacecraft could visit them in sequence, using repeated gravity assists to swing from one planet to the next. Since this favorable arrangement only occurs once every 175 years, NASA was determined to seize the opportunity. They developed what was initially called the Mariner-Jupiter-Saturn 1977 program, later renamed Voyager. The plan included two spacecraft that could potentially visit Uranus and Neptune after Jupiter and Saturn, provided they survived the harsh conditions of deep space. Both probes were launched in 1977 from Cape Canaveral, Florida, just weeks apart. Voyager 2 actually launched first on August 20th, followed by Voyager 1 on September 5th. The numbering reflects the order in which they would arrive at Jupiter, not their launch dates. Each craft was designed to last about 4 years, but engineers added extra capabilities that might allow them to survive and travel toward the far edge of the solar system, or even beyond. In practice, this "if everything goes well" scenario was an understatement. Both probes are still active more than 4 decades later, making them some of the longest-running space missions in history. A crucial factor behind the Voyager program's success was the technique of gravity assists. By flying close to a planet like Jupiter or Saturn, a spacecraft can steal a bit of the planet's orbital momentum, boosting its speed without using too much additional fuel. This was essential. The outer planets are spread over a vast region, and no rocket alone could carry enough fuel to visit all of them in a single mission. These slingshot maneuvers cut travel time, power needs, and fuel requirements. When designing the project, NASA aimed for robust instrumentation that could endure intense radiation around Jupiter, dust impacts, extreme temperature swings, and years of continuous operation. Each craft carried instruments to measure charged particles, magnetic fields, atmospheric properties, and more. They also had cameras for imaging planetary features and moons in unprecedented detail. Early mission briefs predicted that whatever data came back would transform our understanding of the outer solar system. Even so, few could have guessed the magnitude of discoveries and the extended lifespan each probe would achieve. As soon as the spacecraft left Earth, NASA's Deep Space Network (DSN) antennas began receiving early telemetry, basic system checks, low-resolution photos, and engineering data. Flight controllers tested thrusters responsible for orientation, pointed cameras at Earth and the Moon, and calibrated the instruments. From the moment they launched, the Voyager twins were part of a giant web that would grow to include millions of fans and researchers across the planet. The technology behind the missions might seem primitive by modern standards, but for the mid-1970s, they were technological marvels. Each spacecraft had around 69.63 kilobytes of computer memory in total, many times smaller than the size of a single smartphone photo today. This limited capacity forced engineers to devise careful strategies for storing, compressing and sending data. Information gathered by instruments wasn't stored on modern chip memory, but rather on 8-track style magnetic tape recorders, ruggedized to survive radiation and temperature extremes. Communication with Earth depended on a high-gain parabolic antenna that had to stay precisely oriented toward our planet. Voyager 1 and Voyager 2 each transmit with power around 22 watts. Yet by the time the signals travel billions of miles, they become so faint that NASA's massive deep space network antennas must sift them from background noise. These dishes, some 70 meters across, are located in California, Australia, and Spain, ensuring continuous coverage as Earth rotates. Electrical power comes from 3 radioisotope thermoelectric generators, RTGs, on each craft, converting heat from decaying plutonium into electricity. This eliminated the need for solar panels, which would be impractical beyond Jupiter's orbit. Over time, the plutonium decays, reducing power output. NASA has been forced to shut down various instruments over the years to conserve energy, prioritizing the most critical systems. One surprising detail is that each spacecraft can only send data at painfully slow rates, sometimes as low as 160 bits per second when extremely far away. Engineers must prioritize which data gets transmitted first, while some instruments buffer measurements for later playback. Mission teams carefully schedule which instruments receive power and how data is packaged before each long-distance download window. From the start, NASA recognized that these probes might encounter the problems far from home. To prepare, the spacecraft were equipped with onboard fault protection routines and backup computer systems. If orientation drifts or a memory glitch occurs, built-in software can execute safe mode protocols, shutting off non-essential functions and automatically reorienting the antenna toward Earth, assuming the system remains functional. This level of autonomous survival capability was groundbreaking in the 1970s and has been crucial to the probe's extraordinary longevity. In 1979, the Voyagers arrived at Jupiter, the first major milestone of the mission. This giant world, more massive than all other planets in the solar system combined, has a colossal magnetosphere, swirling cloud bands, and dozens of moons. The spacecraft captured images and measurements far surpassing anything possible from Earth-based telescopes at the time. They revealed Jupiter's previously unknown ring, discovered new moons, and recorded detailed observations of the largest moons, Ganymede, Callisto, Io, and Europa. A bombshell discovery was volcanic activity on Io. Before Voyager's arrival, scientists had no idea that one of Jupiter's moons could be so geologically active. Voyager 1's cameras captured actual plumes erupting from Io's surface. Because Io orbits in a gravitational tug-of-war between Jupiter, Europa, and Ganymede, tidal forces generate enough heat to fuel these powerful eruptions. This marked humanity's first direct observation of active volcanoes beyond Earth. The next revelation was Europa's smooth, cracked ice shell. Images showed a whitish surface with long fractures crisscrossing in intricate patterns. Many scientists began suspecting that beneath this icy crust might lie a vast subsurface ocean, raising the tantalizing possibility of conditions suitable for life. Now, after more than 46 years in space, Voyager 1 has sent what may be its final message. The secrets hidden in this last transmission could reshape our understanding of the cosmos. As the probe ventures deeper into interstellar space, its fading signals remind us of an era when humanity first reached beyond its cradle, and how much further we have yet to go. The Voyager data suggested that a liquid water ocean might lie beneath Europa's icy crust, even though there was no direct proof at the time. These findings triggered new questions about alien oceans and the possibility of life in distant realms. Later missions like Galileo and future projects such as Europa Clipper owe a great debt to Voyager's initial glimpses. Jupiter also stunned researchers with its great red spot. Although known for centuries, never before had we seen it in such close detail. The Voyagers revealed its swirling complexity, the interplay of smaller storms around it, and evidence that it had very distinct layers. Jupiter itself turned out to have a seething atmosphere, full of lightning, high-altitude hazes, and an unexpectedly dynamic weather system. The spacecraft also mapped changes in Jupiter's magnetic environment, discovering it was far stronger than expected, with intense radiation belts that posed a threat to sensitive electronics. Beyond the science, Jupiter acted as a huge gravitational slingshot. Each Voyager gained speed from the approach, swinging around the planet in a carefully calculated path. From there, Voyager 1 headed towards Saturn, while Voyager 2 followed a slightly different route, timed for Saturn and beyond. The success at Jupiter firmly established that the mission was on track and that both spacecraft appeared sturdy enough for the next big encounters still to come. Saturn, Mimas, the Death Star moon, and the Valley of Titan came next. After Jupiter, each Voyager continued deeper into the outer solar system. They reached Saturn in quick succession, Voyager 1 in 1980 and Voyager 2 in 1981. Saturn's hallmark is its ring system, so the spacecraft were programmed to capture high-resolution images of the rings from multiple angles. What came back to Earth surprised everyone. Instead of just broad concentric bands, the rings were composed of thousands of narrow ringlets with weird structures like spokes, braids, and scalloped edges. These features arise from interactions with small shepherd moons and gravitational resonances in Saturn's neighborhood. While Saturn's rings grabbed the public's attention, scientists were also excited to examine the planet's magnetic field, swirling cloud tops, and especially its moon Titan. Titan has a thick, opaque atmosphere rich in nitrogen and methane. Earth-based observations had hinted that Titan might be unique among moons, but nobody realized to what extent. Voyager 1 traveled on a path that took it much closer to Titan, collecting critical data about its atmospheric density and composition. This maneuver, however, changed Voyager 1's trajectory. After the Titan flyby, it was flung out of the ecliptic plane, preventing it from heading on to Uranus and Neptune. The Titan decision was pivotal. Mission planners had to choose whether to sacrifice Voyager 1's chance to see more outer planets in favor of up-close data on Titan. They chose Titan. The gamble paid off. Titan's surface remained invisible in normal light. But temperature readings and atmospheric analysis suggested that methane might exist there in cycles similar to water on Earth. Later missions, most famously the Cassini-Huygens orbiter and lander, would unravel huge mysteries about Titan, from liquid methane lakes to possible hydrocarbon-based weather. Voyager 2, meanwhile, took a trajectory that allowed it to continue onward. While it did pass Saturn, it wasn't directed so close to Titan, meaning it could remain near the plane of the solar system. From its vantage point, it discovered new Saturnian moons. One moon, Mimas, earned the nickname Death Star Moon because of its giant crater, giving it a look reminiscent of the Death Star from Star Wars. Meanwhile, the ring observations kept scientists busy for years as they tried to figure out why the rings looked so detailed and dynamic. By the time Voyager 2 finished at Saturn, the concept of a grand tour to Uranus and Neptune was no longer just theoretical. The spacecraft systems had survived two intense planetary environments, Jupiter and Saturn, so NASA extended the mission. With Saturn behind it, Voyager 2 set sail for Uranus, an uncharted region no spacecraft had ever visited. Uranus, an icy world on its side, was reached by Voyager 2 in January 1986. The seventh planet from the Sun, Uranus often receives less fanfare than Jupiter or Saturn, but it turned out to be remarkably different in its own right. For one thing, Uranus is tilted about 98 degrees, essentially rolling on its side like a barrel as it orbits the Sun. Scientists believe a collision or major gravitational event in the distant past caused this strange orientation. Voyager 2's flyby revealed the planet's composition to be significantly different from the gas giants Jupiter and Saturn. Instead, Uranus is an ice giant with large amounts of water, methane, and ammonia locked beneath its cloud tops. The spacecraft measured extremely cold temperatures, sometimes even colder than those on Neptune, which is farther from the Sun. This suggested Uranus emits surprisingly little internal heat. The planet's magnetic field was also weird. The magnetic axis is tilted and offset from the planet's center, creating an oddly twisted magnetosphere that sometimes flaps around unpredictably. The probe gave us our first close look at Uranus's rings, which are fainter and narrower than Saturn's. It also discovered new moons, some with intriguing surface features like fractures and canyons, raising questions about their geological histories. Although the flyby was brief, it remains the only detailed mission to Uranus ever carried out, meaning scientists still pore over Voyager 2's data decades later. While Voyager 2 ventured onward, Voyager 1 had no more large planets to visit after being deflected by Titan's gravity at Saturn. It headed upward, away from the ecliptic plane, its prime activity now focused on measuring fields and particles in the outer reaches. This provided the first extended baseline on solar wind behavior far from Earth. Eventually, its cameras were turned off to save power and memory. But in 1990, before the final shutdown, Voyager 1 captured the famed pale blue dot image of Earth from about 3.7 billion miles away. This single photograph, showing Earth as a tiny speck of light, became an iconic symbol of our planet's fragility and small place in the cosmic arena. Neptune and the enigmas of Triton awaited Voyager 2. With Uranus behind it, the spacecraft continued outward, arriving at Neptune in August 1989, the culmination of the original Grand Tour. Neptune is around 30 times as far from the Sun as Earth, making solar energy extremely feeble at that distance. Yet Voyager 2 found that Neptune has some of the fastest winds in the solar system. One giant storm, known as the Great Dark Spot, resembled Jupiter's Great Red Spot, though later observations showed Neptune's storms can appear and vanish in relatively short time frames. The probe also focused on Neptune's faint rings and its complex interplay of satellites. The biggest surprise was Triton, Neptune's largest moon. Triton was discovered to have active cryovolcanoes venting nitrogen gas, something no one had expected on an object so cold and distant. Triton orbits Neptune in retrograde fashion, the opposite direction of Neptune's rotation, suggesting it might be a captured object from the Kuiper Belt. Its surface was riddled with strange cantaloupe terrain and swirling patterns that hinted at geologic reworking. When Voyager 2 wrapped up its Neptune encounter on August 25th, 1989, it became the only spacecraft ever to visit the ice giants Uranus and Neptune. Its journey, spanning over a decade, had transformed our understanding of the outer solar system and set the stage for future exploration. Even now, as both Voyagers continue their lonely voyages into interstellar space, their legacy endures, reminding us of humanity's first bold steps beyond the familiar worlds of home. The Voyager missions entered a new cosmic chapter after completing their historic grand tour. Having successfully conducted flybys of all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, Voyager 2 exited the outer planet region and joined Voyager 1 in exploring the territory beyond Neptune and Pluto. Their journey now focused on approaching the boundary that separates the Sun's domain from interstellar space. Over the following years, both spacecraft primarily studied the solar wind and cosmic rays far beyond the orbits of the known planets. While NASA's official planetary grand tour had ended, a whole new adventure was just beginning. Scientists soon realized that if the Voyagers could continue operating, they might deliver unprecedented data about the heliosphere, the vast region dominated by the Sun's wind and magnetic field, and its transition into interstellar space. The Sun constantly emits a flow of energetic particles called the solar wind, which extends across the solar system. Near Earth, this wind interacts with our planet's magnetic field, shaping phenomena like auroras. At extreme distances, however, the solar wind weakens and eventually collides with the interstellar medium. The boundary where this occurs is called the heliopause, marking the outer edge of the Sun's influence. Inside this boundary lies the heliosphere, a vast bubble, or more accurately, an elongated structure where the solar wind dominates. Beyond the heliopause, interstellar space is filled with material from other stars, cosmic rays, and the broader galaxy. For decades, scientists were uncertain about the exact location of the heliopause or whether the solar wind would fade gradually. Reality proved more dramatic. The transition occurs in a relatively abrupt region known as the heliosheath, where solar plasma gives way to interstellar material. On August 25th, 2012, Voyager 1 detected a sudden drop in solar wind particles and a surge in high-energy cosmic rays from outside our solar system, the definitive sign it had crossed the heliopause. At that moment, it was over. 11 billion miles from the Sun, becoming the first human-made object confirmed to enter interstellar space. 6 years later, on November 5th, 2018, Voyager 2 followed suit. The data from both crossings surprised researchers. Previous models had predicted certain temperature and density profiles, but reality did not match expectations. The boundary region was much colder than anticipated, and the interstellar magnetic field was stronger than older estimates. The local environment also proved highly dynamic. Shock waves from solar flares could travel beyond the heliopause, creating ripples in interstellar plasma that the Voyagers detected as faint waves. Another intriguing discovery was the possible asymmetry of the heliosphere. Voyager 2's crossing occurred at a different distance than Voyager 1's, suggesting the solar wind and interstellar medium create an uneven, squashed boundary. The spacecraft also recorded a mysterious cosmic hum, a steady 3 kilohertz signal that persists year after year. Scientists speculate it may be caused by background plasma vibrations in interstellar space. The hum's consistency hints at a stable, unchanging condition in this distant realm. though its exact source remains unknown. While the Sun's heliosphere is a local bubble, it drifts within a larger structure called the local interstellar cloud, shaped by ancient supernova explosions. Some theories suggest this cloud is part of an even larger local bubble, a region spanning up to 1,000 light-years, carved out by multiple supernovae over millions of years. The Sun currently resides in this low-density cavity, surrounded by denser walls where star formation thrives. Recent 3D reconstructions from the European Space Agency's Gaia mission reveal that the local bubble's surface is lined with stellar nurseries resembling a cosmic Swiss cheese. Space Agency's Gaia mission revealed that the local bubble's surface is lined with stellar nurseries, resembling a cosmic Swiss cheese. There is speculation that as the Sun moves through different regions of the Milky Way, changes in interstellar density could influence Earth's climate and even mass extinctions. Some astrophysicists propose that denser galactic arms might expose our planet to higher cosmic ray fluxes, though this remains debated. Regardless, the Voyagers provide direct measurements of our interstellar neighborhood, revealing how conditions shift at distances of tens of billions of miles. By the 2000s, both Voyagers had far exceeded their expected lifespans, and technical failures became inevitable. A major crisis struck on the Toulouse, November 14, 2023, when Voyager 1 suddenly began transmitting garbled binary data. Engineers determined that its Flight Data System FDS memory, which stores critical software and telemetry, had malfunctioned. The spacecraft was effectively mute, returning only nonsensical signals. The challenge was immense. Voyager 1 was over 150 astronomical units away, meaning each command took 22.5 hours to reach it, with another 22.5 hours needed for a response. A single error in memory reallocation could permanently cripple the probe. Despite the risks, NASA's team devised a plan to rewrite and relocate corrupted code segments to unaffected memory banks. The painstaking process began on April 18, 2024, with engineers transmitting carefully crafted instructions and waiting days between each step for confirmation. Finally, on April 20th, 2024, the fix succeeded. Voyager 1 resumed sending coherent data, proving once again its resilience in the depths of interstellar space. As the Voyagers continue their solitary journeys, they remain humanity's farthest-reaching emissaries, still uncovering secrets about the universe and our place within it, long after their original mission ended. After months of tense waiting, engineers finally received confirmation that Voyager 1 was once again sending coherent signals. A 5-month communications blackout had ended. This remarkable success story demonstrates how ingenious, patient engineering can breathe new life into aging hardware built in the 1970s. It's easy to overlook just how difficult it is to troubleshoot a spacecraft so far away that you can't simply press a reset button or swap out a faulty circuit board. The fact that memory reallocation worked at all is a testament to the original designers, who included at least some redundancy in the memory modules, as well as to the modern team that devised a creative solution. Even so, each malfunction serves as a reminder that time is running short. Eventually, the radioisotope thermoelectric generators, RTGs, will no longer produce enough power to keep the transmitters active or the circuits warm. NASA anticipates that around 2025, a phased shutdown of major subsystems will begin, marking the slow, inevitable end of the Voyager's operational lives. One of the most enduring and cherished aspects of the Voyager missions has nothing to do with scientific instruments. Each spacecraft carries a golden record, a 12-inch gold-plated copper disc designed to tell a far future discoverer about life on Earth. Spearheaded by a small team, led by Carl Sagan, the record contains sounds of nature, surf, wind, thunder, greetings in for us 55 languages, a curated selection of music spanning diverse cultures, and such 115 images depicting scenes from Earth. It also includes a message from the US President at the time of launch and from the Secretary General of the United Nations, along with instructions on how to play the record. Attached to each golden record is a stylus, along with diagrams indicating the correct rotational speed and orientation needed to decode its contents. The record's cover also features a pulsar map, using the positions of distant neutron stars to pinpoint the Sun's location in the Milky Way. While the likelihood of an alien civilization or a distant future humanity ever finding these drifting artifacts is vanishingly small, the golden records stand as a powerful symbol of human curiosity and hope. They declare, in essence, we were here, and this is who we were. NASA's decision to include these messages went beyond pure science, recognizing that if the Voyagers persist for millions of years, they may become the last traces of earthly civilization long after humans are gone. Whether they are ever discovered or simply float silently among the stars, they remind us that exploration is not just about gathering data. It's also about reaching out, expressing ourselves to whatever might exist in the vast unknown. It's often said that the Voyagers have left the solar system, but this depends on how we define its boundary. If we consider the edge of the solar system to be where the Sun's magnetic influence and solar wind end, the heliopause